Mastering the art of path planning. How artificial intelligence is revolutionizing the process. Have you ever wondered how precisely and nimbly robots maneuver through challenging environments? Are you interested in the technologies powering robots in warehouses or self-driving cars? Come along on a fascinating adventure into the field of path planning, where robot navigation through complex mazes and dynamic environments is being revolutionized by artificial intelligence. How do robots dynamically adjust to changing environments? How does artificial intelligence help robots learn from their experiences? Prepare to learn the insider tricks of artificial intelligence-driven path planning and explore the groundbreaking advancements influencing robotics in the future. Watch now to see the skill of path planning in action and don't miss anything. Path planning is a crucial element in robotics and autonomous systems, influencing the effectiveness, security, and triumph of assignments varying from intricate manipulation jobs to navigating unfamiliar surroundings. Path planning algorithms have traditionally depended on pre-established rules or heuristics, which made it difficult for them to adjust to changing conditions or unforeseen impediments. But the introduction of artificial intelligence has ushered in a new era in path planning, transforming the procedure and opening up previously unattainable possibilities. In this video, we look at how artificial intelligence is changing path planning and making it possible for robots and autonomous systems to go across complicated situations quickly, intelligently, and effectively. Dynamic adaptation. AI-powered path planning relies heavily on dynamic adaptation, which helps robots and autonomous systems navigate through dynamic and unpredictable surroundings. In dynamic contexts like congested warehouses or busy metropolitan streets, standard path planning techniques could find it difficult to handle unforeseen obstructions or abrupt changes in the surroundings. On the other hand, artificial intelligence-driven path planning algorithms perform very well in these situations because they constantly modify their paths based on ongoing analysis of real-time sensor data and ambient input. These algorithms are capable of learning from the past and modifying their behavior in response to changing circumstances by utilizing machine learning and reinforcement learning methodologies. For instance, a robot with a dynamic adaptation algorithm installed can see objects in its route, such as cars and pedestrians, and dynamically modify its course to steer clear of accidents and reach its goals safely. Likewise, in a warehouse setting where impediments could be in constant motion, a robot can instantly modify its course to steer clear of other robots or things. Robots can navigate through complex and dynamic situations with agility and efficiency, thanks to their capacity to adapt to changing conditions on the fly. This eventually enables them to complete jobs with better reliability and efficacy. A future where robots can precisely and easily navigate through even the most difficult settings is promised by the possibility for dynamic adaptation to improve the capabilities of robotic systems in real-world scenarios as artificial intelligence technologies continue to evolve. Uncertainty management. A key component of artificial-powered path planning is uncertainty management, which allows robots and autonomous systems to navigate through environments with imprecise information and unstable conditions. Robots frequently face uncertainty in real-world circumstances because of things like sensor noise, variable environments, and dynamic impediments. This problem is addressed by artificial-driven path planning algorithms, which integrate uncertainty estimation and probabilistic reasoning into the decision-making process. These algorithms can create pathways that balance exploration and exploitation, optimizing information gain while lowering the chance of accidents or failures by simulating uncertainty and risk variables. For instance, a robot with uncertainty management skills can create routes that steer clear of high uncertainty places, including spots with inadequate sensor coverage or unclear obstructions, when navigating through a congested environment. Furthermore, the robot can decide which course of action to pursue to reduce the total uncertainty in its path by calculating the likelihood of various outcomes and potential dangers. By ensuring that robots can operate safely and effectively in unpredictable situations, this uncertainty-aware strategy enhances the robot's dependability and performance in real-world circumstances. Uncertainty management has a huge potential to improve robotic systems' capabilities as artificial technologies develop, offering more resilient and adaptable methods for navigating through challenging and unexpected circumstances. Learning from experience. A key component of artificial intelligence-powered path planning is the ability to learn from experience, which revolutionizes the way robots and autonomous systems navigate through challenging and dynamic settings. Artificial intelligence algorithms allow robots to continuously improve their path planning techniques based on input acquired from previous encounters with the environment, in contrast to traditional systems that rely on static rules or heuristics. Robots can improve their performance over time by iteratively adjusting their behavior through a process called imitation learning or reinforcement learning. Imagine a situation where a robot has to pick up and distribute products while navigating a congested warehouse. To get there, at first, the robot can take a predetermined route or use a heuristic. But as it navigates the terrain, it runs into roadblocks, unanticipated layout changes, and navigational difficulties. By gaining experience, the robot is able to modify its path planning approach according to the input it receives from these interactions. For instance, the robot can learn to dynamically reroute its track to avoid collisions and arrive at its objective more quickly if it comes across a crowded location where items in motion or other robots are obstructing its initial path. The robot gradually learns optimal path planning behaviors that optimize efficiency, decrease risk, and adapt to the unique requirements of its environment by tracking the results of its activities and modifying its behavior accordingly. Furthermore, robots can adapt their knowledge and abilities to a variety of tasks and contexts thanks to experience-based learning. When navigating through a different facility with comparable layout characteristics, a robot that has been trained to navigate through a warehouse environment might be able to employ similar path planning procedures. The ability to adapt and generalize is crucial in real-world scenarios where environments may be dynamic and unpredictable. Robots are able to overcome obstacles, move more efficiently, and reliably accomplish their goals by continuously learning and adjusting from their prior experiences. Robots can also customize their path planning algorithms to suit certain jobs, user preferences, or requirements by learning from experience. A robot in a production facility would promote speed and efficiency, but a robot working in a crowded public environment might learn to prioritize safety and pedestrian-friendly paths. All things considered, experience is a major factor in improving the intelligence, efficiency, and adaptability of artificial intelligence-powered path planning systems. The ability for robots to learn and enhance their path planning skills will only increase as artificial intelligence technologies progress, opening the door for increasingly complex and autonomous robotic systems that can navigate through a variety of difficult and demanding settings with accuracy and agility. Multi-objective optimization. By balancing conflicting goals and restrictions to get the best answers, multi-objective optimization is a sophisticated technique that transforms the decision-making process in artificial intelligence-powered path planning for robots and autonomous systems. The objective of traditional path planning is frequently to determine the fastest or shortest path between points A and B. Robots may, however, have to balance several goals at once in real-world situations, including reducing travel time, preserving energy, averting collisions, and maximizing safety. To tackle this difficulty, multi-objective optimization algorithms examine the trade-offs between various objectives and produce a collection of options referred to as the Pareto front. The finest possible compromises between competing goals, where achieving one goal can mean sacrificing another, are represented by these solutions. Multi-objective optimization gives decision-makers the flexibility to select the best course of action based on their priorities and preferences by offering a wide range of alternatives. Take, for instance, a delivery robot that is traveling metropolis to deliver packages to various areas. The robot might have to prioritize a number of goals, such as avoiding crowded locations, cutting down on energy use, and limiting trip time. With the use of multi-objective optimization algorithms, a set of paths that balance these goals can be produced, enabling the robot to select the most expedient approach in light of delivery deadlines, battery life, and traffic circumstances. Furthermore, robots can navigate through settings with complicated constraints and preferences thanks to multi-objective optimization. For example, a robot working in a hospital setting could have to weigh goals like cutting down on travel time between patient rooms while avoiding busy areas and keeping a safe distance from both patients and personnel. Multi-objective optimization algorithms enable robots to make well-informed decisions that maximize overall performance and pleasure in a variety of dynamic and varied contexts by taking into account many objectives at once. Multi-objective optimization holds great promise for improving robotic systems' path planning and decision-making abilities as artificial intelligence technologies develop. This could lead to more effective, flexible, and intelligent robots that can navigate through difficult and complex environments with accuracy and agility. Scalability and generalization. Robots can apply newly acquired information to new jobs or situations thanks to the scalability and generalization capabilities of artificial intelligence-driven path planning algorithms. Robots are able to apply path planning principles that they have learned in one context to new and unknown settings through the use of transfer learning and domain adaptation approaches. Robots can work in a variety of contexts and carry out a broad range of jobs thanks to their scalability, which eliminates the need for significant manual intervention or retraining. Artificial intelligence is transforming path planning through the facilitation of multi-objective optimization, scalability, generalization, learning from experience, dynamic adaptation, and uncertainty management. These developments open up new possibilities for intelligent, agile, and efficient navigation of complex environments by robots and autonomous systems, opening doors for applications in domains including autonomous cars, warehouse automation, search and rescue operations, and healthcare robotics. PathPlanning has great potential for safer, more effective, and intelligent robotic systems that fit in naturally with our everyday lives as artificial intelligence develops. Subscribe now to stay updated on the latest advancements in artificial intelligence-powered path planning and robotics, and discover how cutting-edge technologies are reshaping the future of navigation and autonomy.